So, good morning, everyone. Please take your seats. You're going to start the first session of today for the survivors. It's getting, the survival curve is really getting low. Perhaps incidence of no-showers, 80%. We'll see. So, good morning, everyone. We're going to start the first session of this Friday, the last day of the program. It's a pleasure to be given the opportunity to chair QSP Pbpk disease modeling session, which has very interesting topics early in the morning after a very nice party yesterday evening. We're going to start this session trying to bring you a slightly different perspective from what has been discussed so far. We have seen new techniques, new methods around AI, machine learning. We are going back to the basics, to the mechanisms, and the speakers will show you some of the efforts in that area. Our first speaker is Joy Leung, who has graduated as a physicist in the US, in China, and has had his postdoctoral time at Georgia Tech in the US, and is currently working at systems modeling and translational biology at GSK in the UK. He's going to present virtual population analysis of a quantitative systems pharmacology, a model of atopic dermatitis to evaluate atopic dermatitis treatments. Joy, please.
Thanks, Oscar, for the kind introduction. I'm Joy Leung from GSK, and I would like to thank the organizers for the opportunity to share my work here. So I'll be talking about our QSP modeling effort in atopic dermatitis, focusing on the virtual population development. Thank you. Okay, so atopic dermatitis is a heterogeneous disease with really complex mechanisms. So the mechanisms include disruption of skin barrier function and activation of keratinocytes in the skin, dysbiosis of the skin microbiota, and involvement of pathogenic bacteria. And so it's driven by disrupted immune responses, mainly the main drivers are Th2 and Th1 cells. And also you have these complex interaction between the sensory neurons, which cause itch, and the scratching, which can further disrupt the skin barrier. So in terms of biologic treatments, the currently approved and late stage biologics include, so they focus mostly on Th2 responses. And the first one that was approved was dupilumab. And it works by blocking the receptors of IL-4 and IL-13, which are important Th2 cytokines. There are more recent anti-IL-13 treatments, including tralokinumab and lebrikizumab. And another Th2 cytokine, IL-31, is also a target for some late stage treatment in late stage development. So the goal of our QSP modeling and also having any kind of pharmacometric modeling is ultimately to improve the patient outcomes, and we try to do this by focusing on the right treatment for the right patient. So we can do this in two broad sorts of way. First, we would like to know the efficacy and focus on the right treatment or target. So the type of questions we ask there is, for example, what is the efficacy of the treatment of interest? How does it compare to standard of care? And then that would inform the treatment line position. And also we can look at additive or even synergistic targets in the QSP model for combination therapy. And the second type of question has to do with selecting the treatment, the right patient for the treatment. And we do this by patient stratification, asking the question whether there's a subgroup of patients in which a treatment works better compared to the standard of care, and whether there are any biomarkers associated with treatment response, or even better, whether there are predictive biomarkers that can predict the response. And QSP modeling is well suited to answer these two types of questions because we are able to link the effects of target engagement to downstream biological processes and ultimately to clinical outcomes using mechanistic knowledge of the disease. So I won't go into the details of the model structure, but on a very high level, so this model is based on the previous model developed back in 2015, and it has been significantly updated by first adding a serum compartment for biomarker readout, and the effects of different Th2 cytokines have been sort of resolved, so we can predict efficacy for dupilumab, and we have added the Th1 pathway and also implemented some clinical score in the model. And so the schematic here shows the main processes included in the model. We have infiltration of microsome allergens, which triggers the disease, which then activates a number of immune cells, keratinocytes, and these produce cytokines that can cause itch. And the scratching can further disrupt the barrier, and this tends to perpetuate the disease. And in terms of clinically relevant outcomes, we can predict things like itch, skin barrier function, a number of cytokine biomarkers, and also the commonly used eczema area and severity index, or EASI score. So here's a list of the main components included in the model. For the cell types, we have the main drivers, Th1 and Th2. We have keratinocytes, and for Th2 response, the main effectors are eosinophils and mast cells. They're important for allergic reactions. And dendritic cell is important for antigen presenting. And finally, we have sensory neurons that can induce itch. So for the main cytokines, we focus on Th1 and Th2 cytokines and a few other mediators. I've mentioned the clinical outcomes, and we have two compartments in the model. Most of the pathology happens in the skin in the model, and there's also a serum compartment for things like cytokine biomarkers. So here I focused on the pathways, the Th1 and Th2 pathways that are important for atopic dermatitis and how it's implemented in the model. So on the left, you can see this is the Th2 schematic focusing on IL-4 and IL-13 as the main cytokines. And these are produced by Th2 mast cells, eosinophils. And they can lead to a range of downstream effects, including more activation of Th2, activation of keratinocytes, disruption of skin barrier by the downregulation of certain barrier proteins, and induction of itch via sensitizing neurons, and activation of eosinophils. And on the right, we have the Th1 pathway in the model. Th1 activation is induced by IL-12, and then the Th1 can secrete a number of Th1 cytokines, including IFN gamma, TNF-alpha, and others. And an interesting point to note is that Th1 and Th2 responses, they are mutually inhibitory. So, for example, IL-4, which is a Th2 cytokine, actually inhibits Th1 activation. So today I'll focus on the development of the virtual patient population. On the left, this is a kind of flow chart of the main stages of virtual population development in a QSP model. The first step is to identify key parameters and sample them between ranges. And we do this via a global scientific analysis and selected about 70 out of the total 500 parameters. And the ranges were selected to provide sufficient coverage for the biomarker data we have. And the next step would be to filter out those virtual subjects that do not quite make sense. And we do this by first collecting the ranges of biomarker in baseline disease. And those virtual subjects that has biomarker levels way outside of those ranges, we filter them out. And then we are left with an initial plausible population of virtual patients. And we still need to calibrate that virtual population. And we do this via a process that we called prevalence weighting. So the idea is to, we now have a pool of virtual patients, but we don't really know how common those patients are in the actual patient population. So we collect statistics like mean and standard deviation of biomarkers and treatment response from published data, and we use that a Bayesian algorithm to match those the model predictions with the data. So here I'm showing the results of the calibration. So the orange box are all the baseline biomarkers and clinical score that we have used for the calibration, and the green part is clinical trial data from dupilumab. So for example, this one is the EC percentage reduction in EC score and percentage reduction in itch. And in each panel, the one on the left is the initial plausible virtual population. And we have the data in the middle. We estimated the distribution using the summary statistics reported in literature. And on the right, that is the calibrated model prediction. So you can see what the algorithm is trying to do is trying to match all the biomarkers and treatment response and the distribution with the data. And then it's in this case is do a pretty good job for most of the biomarkers and data we have tested. All right. So we have a calibrated virtual population. So the next step is to validate the population. And for this, we have selected some clinical trial data of anti-IL-13 that was not used in the calibration. So these are two trials, and I've extracted the mean and calculated the standard deviation from these trials in terms of itch reduction and also EC score reduction. So for the model prediction right now, I'm simply assuming a fixed high target engagement level. And you can see the clinical data on the left. These are from these two trials of these two, both anti-IL-13, and they lie within the range of the model prediction. So the EC score reduction has a similar match here. All right, I think the computer has blue screen on me. Okay, it's rebooting.
Where were we, sir?
Thing is here. All right, good. Thank you. Yeah, I didn't know even a computer can get hangover. Yeah, so now we have a validated virtual population, and so it's time to try to answer some questions, right? So as a case study, I'm focusing on dupilumab and the IL-4 and IL-13 data, IL-13 targets to showcase what kind of applications we can have for the model. So as I mentioned, the first kind of question we want to answer is efficacy-based. So these are the model predictions for dupilumab for a few different endpoints. So we have itch reduction, EASI score reduction, and skin barrier function improvement. And the dupilumab is modeled here via a two-compartment PK model that has been published. And we got IMAX IC50 values again from published data. And we combined the PK/PD model with the QSP model to link the dosage all the way to clinical outcomes. So as you can see, the dupilumab significantly improved all these endpoints, and this is consistent with clinical data. So as a sort of comparison, I've also simulated the case when we just inhibit one of the pathway that dupilumab hits. So dupilumab inhibits both IL-4 and IL-13, but we can deplete just IL-4 or just IL-13 here as a comparison. And generally speaking, IL-13 seems to be a better target, and maybe there's a reason why there are multiple anti-IL-13 in the market now. So it does seem that the combination of blocking both may have some additional benefits as well. So the next thing we look at are biomarker responses to the treatments. So here I focus on just two of the biomarkers. The first one is an IL-31, which is a Th2 cytokine. And so as you can see on the left, for certain virtual patients, that is significantly reduced by the dupilumab treatment, but there's quite a lot of heterogeneity. And about 30% of the virtual patients has significant reduction in IL-31 according to the virtual population predictions. So I've also looked at the Th1 cytokine IFN gamma. So in this case, again, there's heterogeneous response, and interestingly, for about 15% of the virtual patients, you actually get more IFN gamma after dupilumab. And this has to do with the inhibitory effects of Th2 on Th1 activation. So IL-4 inhibits Th1 activation, and dupilumab, by blocking it, can theoretically increase Th1 response and the downstream IFN gamma cytokine. And interestingly, this has been associated with a adverse event in dupilumab treated patients. So the side effect of conjunctivitis, I should say the exact mechanism is still unclear, but potentially IFN gamma inflammation may play a part. So the next type of question we would like to answer with the modeling is on the patient stratification. So here I will just show a very simple example here. We stratify the patient population based on dupilumab response in itch. So we set a threshold at 10% with improvement in itch. And the left, these are the responders according to this criterion. On the right, the red ones, these are the inadequate responders. So we have these two subpopulations we can now look at separately. And here I focus on the biomarker changes after treatment for these two groups. So on the left, you see the IL-13 reduction is associated with treatment response. So that's kind of expected. On the right, we see also IL-31. There's also an association with with the treatment response. So to conclude, we have developed a QSP model of atopic dermatitis, and we have generated a virtual population for that. And we calibrated and validated the model with baseline data and also dupilumab and anti-IL-13 data. And the few take-home message for in terms of dupilumab and its targets, the IL-13 pathway seems to play a bigger part, and it could lead to increased Th1 inflammation that are associated with side effects. And finally, IL-31 seems a promising biomarker to be associated with dupilumab response. So for ongoing and future work, we're working on a PK/PD model for anti-IL-13, and then combining that with the QSP model to improve the model validation. And we would like to understand the mechanism of the dupilumab inadequate response more closely, and identify predictive biomarkers. And finally, we're interested in evaluating new combinations of different targets to enable prioritization of combination therapy. So with this, I would like to thank my colleagues, and I'm happy to take any questions.
Thank you, Joy, for the presentation. We have time for a very quick question, and I will invite others who are willing to do that in the coffee break if needed. Please, introduce yourself.
Yeah, Wilhelm Hüsinger, University of Potsdam. And thanks for the very nice talk. I have two questions, two short questions. One long question regarding the prevalence weighting. So I would expect it's not a unique process. Do you repeat it several times to see how it impacts your results? And the second one would be, I would expect that you only would do the prevalence weighting in order to compare with already existing study results. But if you want to analyze in more general terms, I would expect that you do not do it, because by prevalence weighting, you confine yourself to the study population that was used, and your virtual population could be much broader.
Yeah, thanks. That's a great question. So I think I have some. I can show the slides now.
Quick answer as well, please. I suggest that you answer the questions off the table, please.
Okay. Yeah. So yeah, this just shows more information of what the algorithm does. So I didn't do repeat it systematically, but I did try initialize it, the randomization a few different times, and there's some variability, but the main results are similar. And then I think the part about whether we want to fit to a certain clinical trial, I think that's a good point, because that is actually one challenge we have. Different clinical trials, even phase 3 trials, they can differ quite significantly. So we are currently developing a method where we sample from the whole virtual population to get the same N with the trials, and then we can try and bootstrap that multiple times, and then compare with the different individual trials.
Okay, thank you.
Thank you very much. We have to move on. Thanks, Joe, for your nice presentation. I would like now to invite the second speaker, Natalia Riva, who is a postdoctoral fellow with Professor Iñaki Troconis in Pamplona, and she has specialized in pediatrics and is working currently in chronic hepatitis B, and we'll be presenting interesting story around the expanding of quantitative systems pharmacology and model framework for acute hepatitis B in chronic infection. Natalia, please.
Thank you. Thank you, Oscar. Good morning, everyone. Well, thanks for the introduction. This is a scientific collaboration between Janssen and University of Navarra. And this is the outline that I'm going to follow with a special focus in step 5 and 6, expansion of the QSP model and creating a virtual population for chronic hepatitis B. So to start with, hepatitis B is an infectious disease caused by the HB virus, which affects around 300 million people worldwide, and it's vertically and horizontally transmitted. When adults are exposed to the HBV, around 95% spontaneously clear the acute infection, while around 5% progress to chronic disease, which is a frequent cause of cirrhosis, hepatocellular carcinoma, and death. Unfortunately, a definite cure doesn't exist, although a functional cure is feasible, which is defined as a sustained loss of detectable viral proteins, specifically the S antigen, and HBV DNA viral loads in serum. With the current standard of care therapies, the rates of functional cure are very low, leading to intensive research in this area to obtain novel therapeutic strategies. Different viral and non-viral biomarkers exist to monitor the progression of the disease. For instance, traditional biomarkers, such as those in the figure, account for the exposure to HBV, replication, and the stage of the disease. Other biomarkers are also used to evaluate the humoral immune response of the patient against viral proteins. And also, of course, we have disease biomarkers such as ALT values to evaluate liver function. New biomarkers have emerged in the last years to account for transcriptional activity and reservoir size, which are the RNA loads in serum and the core-related antigen, given the different conformations that the viral genetic material may adopt after infecting the hepatocyte. The cccDNA is the most frequently obtained conformation of which is the covalently closed circular DNA, is very stable and highly transcribed to produce all viral proteins, while integrated viral DNA within the host genome is less actively transcribed to only produce the S antigen. So different biomarkers account for different viral processes, and to integrate them, a modeling exercise is required. Different mathematical models have been published in literature with different model complexities, mostly data-driven models, but so far there are no models that simultaneously account for integration of existing set of biomarkers, the adequate degrees of mechanisms and contribution of the immune response to the chronic disease, and viral dynamics with enough granularity. This motivated us to develop a QSP model for acute hepatitis B, which consisted of 3 compartments: lymph, liver, and plasma, and contains elements of the innate response, elements of the adaptive cellular and humoral response, and also a modulatory component on cytotoxic T lymphocytes, leading to CTL exhaustion and proliferation inhibition. In terms of viral dynamics, the present structure appears very simplified, leading to the opportunity for expansion of the viral dynamics. So we aim to expand the model considering more granular viral dynamics and including those elements that are relevant for the chronic disease, and to create a virtual population to drive the system towards chronic status and account for all the initial conditions of different entities in the model. So we expanded the model by incorporating the proliferation of healthy and infected hepatocytes, and we also incorporated hepatocytes containing cccDNA and a subtype of a hepatocyte, infected hepatocyte containing cccDNA and integrated DNA. In addition, we also included transcription processes, retrotranscription processes from pregenomic RNA to give DNA variants, and translation to all viral proteins with the corresponding distribution to blood to be detected as biomarkers. We adapted the immune response to account for innate response inhibition of transcription. To account for the inhibition of transcription of to viral RNAs, cytotoxic effects on both infected hepatocytes type 1 and type 2, and the production of antibodies against RNA variants and E antigens, which were not included in the previous structure. So here, as a recap, here I show you all the traditional and new biomarkers that I commented previously in the model structure. So these model structures provides also the drug target sites to potentially evaluate the effect of different therapies, such as the standard of care therapies, nucleotide analogs, on their specific target sites, the HBV polymerase, and the inhibition of retrotranscription, but also provides a framework to evaluate combination of therapies and different approaches. So the model building was based on ordinary differential equations, and we defined typical values of parameters by reusing some of them from the previous QSP model. Some others were extracted from literature, and others were calibrated and derived using pathophysiological knowledge and the implemented model. To ensure that the model was still capable of reproducing the acute infection, we extracted data coming from patients undergoing the acute infection, and we confronted this observed data. Each panel is a biomarker. We confronted this observed data with model predictions, which are shown in solid black lines, and we concluded that the expanded model was still valid to describe the time course of the acute infection. So far, what we have is a model structure that is able to reproduce the acute infection, but we also know that chronic patients have certain characteristics here represented by the levels of the patient's biomarkers, such as those in this list. But so the first question that arises is, how will we transform the acute scenario into the chronic scenario? And we will do so with the same model structure, but assuming that the differences are given by model parameters and initial conditions. So the second question is, how would we identify that set of parameters that drive the system towards chronicity? We will do this by establishing a link between the model structure and biomarker levels in real patients, and creating a virtual population on which ultimately we will implement the treatment and evaluate the performance. In the next slides, I'm going to focus in these processes. So we follow a workflow for the creation of a virtual population by defining the variables of interest, the biomarkers, and their pathophysiological ranges at baseline, previous to any treatment. Then we select the sensitive model parameters and input ranges. We simulate parameter vectors from a predefined uniform distribution and boundaries. And then we select the most suitable virtual patients with predicted biomarkers within the pathophysiological range defined in the first step, with adequate correlation between biomarkers and an adequate percentage of infected hepatocytes in the liver. So we first define the biomarkers pathophysiological ranges at baseline according to literature and clinical trial data. On this case, I'm showing the standard of care naive patients in their E antigen positive status of the chronic disease. Each panel is a biomarker, and in gray, we can see the ranges of each biomarker. Then we perform a local sensitivity analysis, and we identify 50 model components with greater impact on biomarker, including model compartments, initial conditions, and also kinetic parameters. Here I show the distribution of those sensitive parameters and boundaries according to literature and or arbitrarily defined in case data was not available. So this set of parameters feed the model, and through simulations with the model over a period of 6 years, we obtain thousands of profiles of each, let's say, potential virtual patients for each biomarker. Then, applying the criteria of the pathophysiological range of each biomarker, we filter and selected the most suitable virtual patients according to the first criteria. Further criteria for selection was based on adequate correlation and adequate percentage of infected hepatocytes. So in this slide, I present the biomarker profiles for the representative virtual patients, those selected virtual patients. Each panel is a biomarker, and in solid black lines, I present the median and range of each of them. So we can see that a fair description of biomarker was attained. In addition, we also observed that a percentage of virtual patients also evolved to a new number of hepatocytes, which could be interpreted as cirrhosis or death of those virtual patients. And this was in accordance with reported values in chronic patients. We also observed a percentage of a spontaneous functional cure, which also occurs in real patients with a comparable frequency. So in conclusion, we were able to expand the HBV model, incorporating additional granularity on the viral dynamics, and adapted the immune system with confirmed backward compatibility with the acute model. We also created a virtual population for the chronic HBV, which was essential to drive the system towards chronicity. We provide a framework here to estimate drug effects of the standard of care therapies, but also other therapeutic agents, as well as immune modulatory therapies. So this HBV QSP modeling framework represents a differentiated scientific and bioinformatic tool that contributes to the understanding of the disease. So with this, I want to thank the team for their support and patience, and I want to thank you for listening.
Thank you, Natalia, for this excellent presentation. Again, the floor is open for questions. Please.
University of Potsdam. Thanks for the very nice talk and illustration of how you generated virtual populations. I've one question regarding the sensitivity analysis, which was the basis of choosing parameters that you then put variability or uncertainty on, if I correctly understood. The sensitivity analysis was based on a univariate approach. So you just varied one parameter and looked how sensitive the output is. So I was just wondering, because we observed that it could be that a single parameter has a big impact, or many parameters have just who individually have a small impact, but in total have also a large impact. So it could be that you are missing out patients that have variability in a lot of parameters, but you wouldn't have identified them by your sensitivity analysis. Did you look into this, or?
We have looked into this, but we could also double check, because this is an interesting question. Thank you. So we modify, but we also compare our previous sensitivity analysis, and as we observe the effect on different biomarkers, and the steps in between could impact on the levels of the different biomarkers, or some others may not, but we also incorporated some parameters that may be relevant, such as the integration of the concept of integration of the DNA. So yes, we could consider your suggestion.
Yeah. Or to put it differently, I think you don't need this step. You could just put variability on everything, because then you can double check with your biomarker levels. I think that's a very nice idea. Yeah.
Thank you.
Okay.
Yes.
Nick Holford, University of Auckland. Well, that was a tour de force. I really enjoyed that. Woke me up this morning. A complicated business, but I wanted to put a general remark on what you call virtual populations. That's how you described it, which is fine. The virtual population for me begins at time zero, and then after that it's a description of disease progression. So it's just a terminology issue that I would have more quickly appreciated what you were going to talk about if you described it as a disease progression model rather than a model for a virtual population. The virtual population starts at the beginning and then evolves over time.
Indeed, we have to do a simulation for a long time to achieve a stable disease, which is what a patient had when they are chronic, because you sometimes don't detect the infection at the beginning. It may be very silent. It is a silent disease. So we didn't aim to do a disease progression model, but we really needed a stable amount of each biomarker to be accounted as baseline conditions.
Okay. You didn't aim to produce a disease progression model, but from my view, you did. So congratulations, unexpected outcome. And a kind of a follow-up question to that. So imagining it is a disease progression model and it's showing the progression over 6 years, have you considered that there may be other events, important events that occur in the patient's life that would perturb the simulation? Because the way I see the simulation, it just starts at zero and you just solve the equations over time and there's no new events that might come in. And I can't tell you what the events are, but maybe having an intercurrent COVID infection which might affect the liver.
Yeah, there are many covariates that are very interesting to evaluate. This is the case for an E-positive patient. There are 4 stages of the disease, so we could consider different scenarios, but for instance, vertical or this is a typical horizontal transmission, but we could consider like different covariates, for example, some resistance in the genotype of the virus that could be incorporated, but we couldn't consider now. So this is just.
But it's more a time varying covariate, if you wish. So a new event occurs, a COVID infection, for instance, as an example, which happens at some point.
Yes, we could incorporate that by affecting the immune system, which has like an innate response, also adaptive cellular and humoral response. So we could like interplay with that.
Well, anyway, congratulations. A very good model.
Thank you.
Thank you. Thanks, Nathalie, for your nice presentation. We now go to the last speaker, Robin Michelet, who is a consultant at Pbpk, a senior scientist at Freie Universität Berlin, and he will be talking about the development and application of a minimal physiologically based pharmacokinetic modeling framework to predict tumor penetration and receptor occupancy. Robin, the floor is yours.
Thank you very much for this introduction, and thank you all for being here after yesterday. I will indeed, if it comes up, one second, I would say. So I will talk about the application and development of a minimal physiologically based pharmacokinetic modeling framework to predict tumor penetration and receptor occupancy. As already said by Oscar, I'm both working at the Freie Universität and at Pbpk, but this particular work was done together with Pbpk and Boehringer Ingelheim, and I'm really looking forward to show you what we've been doing. It was together with my colleague Klaas Petersen at Pbpk, colleagues David Busse, Alejandro Perez, Gazal Montesseri, and Andrea Tille at Boehringer Ingelheim, Mark Huisman, Willemien Menke, and Iris Miedema at Amsterdam UMC. So I already acknowledge them now so that I don't have to do that at the end. Here we go, very good. So we can skip this, yeah, here we are. So the framework, the background of this project is something called Project Optimus. Yeah, there we go, okay, great. I was actually expecting Project Optimus to be more present here at Page, and maybe it will be next year. It's a recent initiative by the FDA to move dose selection in oncology away from the maximum tolerated dose paradigm towards really going very early towards efficacious doses and not just giving as much as we can without, let's say, intolerable side effects in these vulnerable patients. This means that very early on in drug development, we need to integrate knowledge we have about the compound in order to get an idea about what the hell. So the presentation here is going completely different than there, but just bear with me. I think Joey was right that the computer also has partied yesterday. Yeah, here we are. Can we stay on the slide now? Let's see. Okay, so this means that we need this knowledge very early on in drug development, and at that stage, as we are around phase 1, we don't have that much biomarker or tumor response or efficacy data available. So alternatively, we can try to get some knowledge about how much of the drug is actually reaching the tumor, reaching the target, and then engaging with the target receptor. But that brings us to another challenge. How can we know how much of our drug is actually at the tumor? How can we measure receptor occupancy in vivo? One way of doing this is the use of radio-labeled compounds and measure them at the target site using positron emission tomography or PET scans. So the principle is depicted here, where a radio-labeled compound, which can be labeled with carbon, fluor, zirconium, dependent on which half-life you want, and this depends on the compound you're investigating, of course, is injected into the patient where these positrons interact with electrons in the tissue, emitting gamma rays, which can be detected by your 3D PET scan detector, which gives you an image, which can then be translated to quantitative data, which we as pharmacometricians can use to get an idea about the concentrations at the target site. So what we get from these kind of experiments are radioactivity measurements. So we need to transform them in some way to make them work in our modeling framework, let's say. So what is typically done is that these radioactivity measurements in becquerel per gram tissue or per milliliter blood are corrected for the amount of radioactivity that is administered and for the natural decay that is happening to these compounds in order to give you an observation in injected activity, percentage of injected activity per amount of tissue. When we correct this for the mass of radio-labeled dose that we administer, we can transform this, as you see below, from activity towards something we can use, we know, microgram per ml or per gram tissue, assuming 1 gram per liter of density of tissue. This is very nice. This is a new source of information that we can use in our models, but one caveat here is that we will get total tissue concentrations or total tumor concentrations. So we're not considering here any distributional processes within the tumor, for example, within the different subcompartments. So if we want to use this to know how much is exactly at the receptor, we still will need some analysis strategy to leverage these data in order to help with decision making. And that's exactly what we try to do in this project, try to set up such an analysis strategy. And the strategy we chose for here is a minimal physiologically based pharmacokinetic modeling framework. So to develop this framework, we start with a case study, the first one of hopefully many, and I hope I also encourage you to start applying these kind of frameworks in your data sets in your companies or universities. So the case study was an anti-LAG3 compound. LAG3, or lymphocyte immune inhibitory receptor, is a receptor expressed on T cells, which in normal life inhibits the immune response, and in this way allows tumors to escape attack by T cells. So if we inhibit this receptor, we can reactivate T cells, and in this way try to reduce tumor growth or even go towards tumor shrinkage. It's a funny receptor in the way that it has an internal pool present within the T cells, which allows it to translocate and re-express very rapidly after internalization. So it has been reported within 1 hour. And when a compound binds to this receptor, it also internalizes within the cell, which will give rise to some interesting processes we will need to consider in the model analysis, which I will touch upon later. The study we had at hand with this anti-LAG3 compound, BI75411, is as follows. First, radio-labeled compound together with a little bit of cold compound was injected in order to really see the kinetics of this monoclonal antibody at the target site. And afterwards, it was combined with a higher unlabeled dose in order to really block all the receptor and see what the difference in target uptake would be. Within this study, we saw already that clinical plasma pharmacokinetics between unlabeled and labeled compounds were completely comparable, which is of course a prerequisite of analyzing these data. And also target binding was found to be comparable between unlabeled and labeled compounds. Another interesting fact that I didn't tell you before about zirconium-89, so the label that was used on this compound, is that once it internalizes into a cell, it doesn't get out. So it residualizes and stays there emitting radioactivity. So you can again imagine from a data analysis point of view that this is, let's say, interesting. Okay, how can we analyze these data? Typically, we have the two standard approaches. Also moving away from this depiction, but still to get some understanding of what we try to do. So typically we have either cell mechanistic or data-driven empirical models, or full-blown Pbpk or QSP models, also as you saw in the previous two talks. What we are trying to do here is a bit of both, where we use a minimal Pbpk approach, using data-driven parts of the model where we can, and for the tissue of interest, in this case a tumor, using a mechanism-based, physiologically based part of the model. Our base model, our starting model, was such a minimal Pbpk model called the Lindauer minimal Pbpk model, which you see depicted here, where the top is depicting the plasma pharmacokinetics really as a classical two-compartmental model informed by individual plasma PK from the patients we had in our study, and the bottom part is informed by biological knowledge, where we really try to describe the tumor in its different subspaces using the neonatal Fc receptor rescue mechanism from endosomal clearance, using lymph flows, and so on and so forth. So this model was already put in literature before, parameterized on different compounds, and we try to see if we use our transformed radioactive concentrations and just try to see whether we can predict them with this model, what happens. And that's what I try to show here. So of course for the plasma, which is depicted in red, this model works fine. It's driven by the individual PK we have in our study, so it makes sense that these data are described well by this model. However, the tumor concentrations, which are here a priori predictions, they are under-predicted. And if you think about the model structure that I just showed and the processes I was describing, it makes sense. We're missing some things that are not here, which are peculiarities of LAG3. And we, of course, also realized this and went into a model extension step to include these processes. And I will take you step by step through what we actually did. So here again, our original base model where we started from, where the tumor concentrations are the sum of the three compartments you see there. The first thing we did was adding T cell space to take into account that our target is actually expressed on T cells, and afterwards the compound is also taken up into T cells. So we need to have a compartment to keep track of this. As said, once bound to LAG3, our monoclonal antibody internalizes within the T cell. So we luckily had some data from Boehringer and Ingelheim from in vitro experiments from which we could get an idea about what the half-life of internalization was, and we modeled this then as a first-order process with a rate constant of around 0.3 per hour. I told you that zirconium-89 residualizes, so it stays in the T cell, which means that the labeled part of our complete administration will stay in this compartment and keep emitting signal. It will be part of the measured concentrations. However, the cold part will just be removed once it enters into the T cell and will not be part of our measurements. So to account for this, we separated out our Pbpk model into labeled and unlabeled monoclonal antibody, basically doubling the amount of equations to follow the two species separately. However, we did see that the labeled compound did not stay forever within our system, because of course T cells, they don't stay forever there. They are mobile and they have a turnover rate. So in order to take into account removal of the radiolabeled compound by T cell turnover, we took into account a half-life of an activated T cell of around 3 days and included this as a decay process for the radiolabeled compounds. Lastly, we included what I described before, the recycling of LAC3 back to the surface and the presence of an internal LAC3 pool, which allows for this very rapid re-expression or translocation of the receptor, so a rate constant of 0.3 per hour. These are a lot of processes and parameters to add to the model again. So at this point in time, we performed a global sensitivity analysis on all parameters present in the model based on Sobel's index. And here you see the 5 most sensitive parameters, the most impactful parameters. So basically what we did was varying the entire parameter space over a large range of possible parameter values and looking at the different concentration predictions and performance metrics in order to figure out which parameters were actually important and which were less important. The take home here is that especially LAC3 related parameters and the reflection coefficient in the model were very impactful. And when we looked at the parameter space given by this global sensitivity analysis, it was suggested from the predictivity metrics that a 30% lower reflection coefficient would actually be much better to predict the tumor concentrations. And this made us think, okay, what does this actually mean in this model? And it made us think to extend it with the 2-pore paradigm, so taking into account that monoclonal antibodies can have both convective and diffusive processes. And indeed, when we expanded the base model that we had with all the processes there with a 2-pore paradigm, we saw that if we use it to approximate reflection coefficient, that indeed a lower reflection coefficient was calculated than the default value which is present in the base model. So it was a very nice finding from this global sensitivity analysis. The final model up till now is performing a lot better than the one we had before. It is still not perfect, as you can see here on the right-hand side compared to the left-hand side. On the bottom, you see the quantitative metrics describing the model performance. So we have vast improvement in all of them. But of course, you can only jump so far within a priori model, and individualized parameters or better information about LAC3 and target expression would improve these predictions even further. But still, with this model as such, we were able to reproduce tumor to plasma ratios that we observed in all patients in this clinical study. And here, just shown for one ID, we were able to reproduce both the radio-labeled tumor concentrations, the plasma concentrations, plausible receptor occupancy profiles, and also non-labeled concentration time profiles. So this, as a first achievement of this framework, made us very happy, and then made us think also of what are ways forward, how can we apply this framework further, what did we learn? So first of all, we think this minimal Pbpk framework is really something that we could use to capitalize on these data early on in drug development in order to, at an early stage, predict receptor occupancy and in this way support dosing decisions for phase 2 and so on in the drug development of these monoclonal antibodies. In this project, we saw that not so much the characteristics of the compound, but more so of the target have a big impact on how the model is behaving and how tumor penetration is occurring, and also in other projects with other compounds, we saw similar things. So it's maybe a good message for drug developers out there to not only focus on optimizing KD and FcRn binding, but think also about the target you have and what you expect of target abundancy, local target expression, and target turnover. And lastly, here we were just using a priori predictions for the population. These would of course be much better if we would use individual parameter estimates incorporating IIV, and maybe we could use, for example, individual target expression. This might be more of a wish, but still it would help to give better individualized receptor occupancy predictions. Next steps that are ongoing are really testing this framework a little bit more. We're using other compounds, some a little bit simpler, some a little bit more complex. And we're also looking at preclinical experiments where we can actually directly measure receptor occupancy in order to show whether this framework is working and actually doing a good job in this final finding. The results of this, I would invite you to come in November to ACUP, and there we will show you how this is going. We will also use it further on to support further clinical projects and really ongoing drug development of these monoclonal antibodies, and go back to the biodistribution guys and help them to design these PET imaging studies, both with regards to dosing and sampling times, in order to then come back to more predictive models. So this is also really nice that we have this collaboration ongoing with the people presenting the data, creating the data, knowing where it's coming from, and in this way having, as I always like, a nice learn, predict, confirm paradigm going on. With that, I will close here. I already acknowledged everyone that I needed to, apart from the page organizing committee, so thanks a lot to you as well, the study participants, and of course, all of you for making it here and listening to me talk about receptor occupancy. Thank you very much for your attention.
Thanks, Robin. Thank you for this very nice overview. We have time for a quick question.
AstraZeneca. Thank you for this very clear presentation. So I have a technical question. So you did the global sensitivity analysis, and you finally get some index of different parameter sensitivity. And then you use this, infer the, you have 30% somehow.
Lower reflection coefficient?
Yeah, some of the coefficients you underestimate. I don't understand how your sensitivity index can inform this thing. Can you maybe elaborate?
Of course. So in the sensitivity analysis, we used a matrix of all the possible parameters in a large range of values. And we looked both at the sensitivity in really the predictions, so tumor concentrations, plasma concentrations, hot, cold, and so on and so forth. But we also looked at how, for different parameter values, the performance metric changed. So the absolute fold error, the average absolute fold error, and the root mean square error. And this way you can get an idea about which combinations of parameter values are having a better performance than others. It's a very crude pre-estimation, let's say, but we didn't use it, of course, to define the values of these parameters, but just to look, okay, in which part of the parameter space do we need to be to describe the data better? And can we learn something from that? And in this case, the vascular reflection coefficient was really clearly signaling that the model, it was too high. And then we thought about what this meant. And in the original parameterization, no two-pore paradigm was included. So we checked what would two-pore actually do, and calculating the reflection coefficient using the two-pore formalism got us also a lower reflection coefficient, just as said by the sensitivity analysis. So these two pieces of information together then really prompted us to include the two-pore paradigm within this modeling framework. I don't know if that answers your question completely, but...
Seems like you answered.
Yeah,
thank you.
Thanks a lot for the question. Robin, thanks a lot. Thanks. We have to move on. Thank you very much. So we are now going to the next step, which is the announcement of the next meeting in 2024. But before we start, I'd like just to remind the community that Page will be sending reminders. There will be an opportunity to bid for a location in 25 and 26. So if anyone wants to adventure to make a proposal. We'll be circulating the terms, what is required, and we welcome to submit proposals later this year. Yeah, we will send out email with the details to all of you, and those interested can apply. So we will now basically ask the group from Paolo Mazzei and his team, Menarini, who will be hosting next year's meeting. And Paolo, I think you can come.
So thank you, Oscar, for this introduction, and good morning. Good morning, everyone. I'm very glad to introduce you to the discovery of the location of the 32nd page edition. The team of scientists, clinical pharmacologists, pharmacometricians who contributed together with AFEA and with the support of the scientific steering committee of the organization in selecting the new, in contributing to select the new location, is working in the in oncology R&D of an Italian-American company, Menarini Stemline. So, surprise, surprise, the new edition will take place in Italy, in one of the most famous travel destinations in the world. Any guess? So let's discover together in this short video. So join us in Rome on June 25th through the 28th. Rome, as you may imagine, is well connected to other European capitals and to the whole world via the international airports of Fiumicino and Ciampino, and is also directly connected to all top Italian tourist attractions via the domestic networks of high-speed train, approximately 1 to 3 hours to all the major Italian cities. Our conference will be hosted by one of the most prestigious convention centers in Rome, Gife Palace Hotel, located at approximately 15 minutes from St. Peter's Basilica. The hotel is very well serviced by public transportation and offers more than 700 rooms that you can book for your staying during the conference. We are basically very much convinced that you will enjoy attending Page 2024 in Rome as we did organizing. So, arrivederci a Roma. Thank you very much for your attention.
Before we go for the coffee break, I would like also to take the opportunity, because people will leave later on, I think it will be very important for us to acknowledge the contribution of the local organizing committee of La Coruña. I'm trying to get hold of Isa, Marival and Anna, who contributed clearly to the event, and even if they're not around, I don't see them, I ask them to come to the front. I'd like a clap of applause to the organizers, and I would like to ask you to come back at 10:55 for the next session, which will be chaired by Siv. Okay, thank you very much. The Lou Shiner students, can you please come to see me at the secretariat at the reception, please? Lou Shiner students, please come to the secretariat to talk to me in a few minutes.